Well, welcome to a Tektronix webinar. I'm pleased to be here with Steve Sandler, and we're going to talk today about how to better manage the AI data center energy demands through improved power integrity. Before we get started with the agenda, I'd like to introduce myself and then turn it over to Steve for an introduction. So I'm Chris Loberg. I work here at Tektronix in our headquarter location in Beaverton. I'm responsible for our mainstream scope business operations, and I've got a long career in test and measurement, working with everything from optical to datacom, and now focused around power integrity. And I'm really pleased to introduce Steve Sandler. Steve?
So my name is Steve Sandler, and I'm the managing director at Picotest here. And I spent my career in power electronics and power integrity, almost 5 decades worth. And today it's all about AI. I'm sure you guys are all seeing that too. And so I'm really excited to join Chris today to talk about what's going on with AI and what pressures is it putting on us and how we're going to meet the demands.
Thanks, Steve. This is going to be fun. So let me go to the agenda slide. Um, we're going to spend some time going back and forth talking about common pain points and what's popping up as AI gets integrated into cloud computing and the data center. Then we're going to spend a fair amount of time just going deeper into the power design and validation focus. If we can combine the worlds of design with validation and get focus around how to make improvements for better efficiency with the inclusion of AI, then I think everyone's going to come out in a winning place. And then we'll follow up with, what to look out for, where you can gain that measurement insight. Steve's brought a lot to the table. He's got a lot of experience dealing with customers that want very defined and understandable insights that can help them move forward. And he's going to share some of his best practices. And then we'll do a summary. So let's start on the pain points. I think to get started, it's pretty interesting to see the impact that AI is having on data center efficiency. There's a lot of news out there right now. Most of these news items are very common. If you're reading just even general news, not even engineering news, you'll see that the presence of AI is really impacting data center energy use. And the chart below is something Steve and I kind of collaborated on. And when we look at the technology that's here today with our non-AI server CPUs and the wattage that comes from that, the watts are increasing substantially at the cabinet level in these data centers, and that is causing a lot of concerns out there. So, Steve, anything to add to this news story here on AI and the data center?
Well, I think you nailed it, but one of my focuses is this impedance column that says that, our board impedances have fallen pretty quick. We're down to 20 microohms now, and it's getting to the point where it's difficult to measure. And we're talking about, board level currents of 2000 amps. And I can tell you that I'm talking with my customers and, they're laying out what they think their 5-year plan is. These numbers aren't going to be going down anytime soon. Um,
No, they're
we got
not.
our we got our work cut out for us, and I think it's going to be really challenging, and I think it's also going to be fun.
Speaking of challenges, Steve, here's some of the common challenges we've seen. And I'm going to just pick on a couple here. I mean, really getting an understanding of how to measure large signals, because there's large signals coming in now. I mean, really intense in terms of the large signal size, but then watching small signal stability in the PMIX and the core. The other one I'd like you to kind of comment on is the power dissipation issue. That is becoming bigger and bigger. So, a couple of observations there, Steve, for you to take comment on.
Yeah, not it's just a couple of bullet points, but there's a lot, right? I mean, that's a lot.
Yeah.
The first thing we're seeing is this really is a new frontier, and in my entire career, I don't think I've seen many conditions that were like this, where everybody is sort of in the same boat, trying to figure it out as we go along. There really isn't anybody that just knew how to do this. Maybe I'm a little bit ahead of the curve, but we're all kind of learning together. there's a lot of detail in the difference between small signal, which is how we define impedance, and most of our design is based on target impedance, which is small signal. We talk about control loop stability, which is small signal, but then we're banging around thousands of amps. That's certainly not small signal. That's large signals.
Yes.
And so we're confronting these situations now where we really need to be able to do both, and we need to understand what it is that the data means. How do we actually get usable data out of it? The large signal and small signal don't agree with each other, but they each tell us something. And how do we tease out that data? And you're right. I mean, power dissipation is a huge deal. Right now, we're doing, our designs and high speed stuff at around 10 watts per square millimeter. And trying to get the heat out of these devices
Mm,
is absolutely bonkers, even in single level. And now we're seeing customers that are building 3D stacks of chiplets. And so you got to cool that whole stack, and there's serious power in it. So how are you going to get the power out? It becomes
yeah.
challenging. I guess that word keeps coming up, but I don't know of a different word for that. What a challenge.
Good point. And I think for the companies that are doing this work at the design level, just making sure that what they deliver to customers that are putting these cloud computing systems together has got to be reliable and predictable in terms of understanding the estimates for power capacity once installed, getting an understanding of what power equipment's needed to handle that increased power load when these do get adopted. And I think, in my opinion, it comes back to having good specs all the way back into how to specify all the components that are going into these systems in the power delivery network's design, and then having those come out over time in a completed system so that you can communicate to the operators of these data centers when those systems are installed that you have a very accurate estimation of capacity and prepare for the heating and cooling required with these increased high watt systems that are being dropped in.
Yeah, that's a good point. One of the things that we're seeing is that there's still a lot of specsmanship going on. And of course, there's always been
Yeah.
specsmanship, right? A lot of this is marketing. You should buy my power module instead of his because look, mine is more efficient, right? Um, but not everybody measures them the same way. And certainly not everybody measures them under the same conditions. So, hey, we have this module and it's 93% efficient. Yes, 93% efficient at 40% load, but what does it look like at 100% load?
Yeah.
Um, looks a little bit different.
Right.
And well, we normally operate at about 40% load. No, actually you don't. You operate at 100% load at a 40% duty cycle. And so trying to tease out what the data sheet and spec is actually telling us
Yeah.
versus what it is that the manufacturer wants us to understand, those are kind of two very different
Yeah.
things. And I think we're just starting to learn that now and just put it on the pile of problems that we have is trying to tease out, what's signal and what's noise from the data
Yeah.
that we just got
Yeah.
pushed.
So critical. When we talk about specmanship, it brings to mind a comment I heard at a startup doing AI work in a data center cards, and they said one of our banner specs. We use banner spec a lot in the test equipment business, but banner spec is operations per watt. How can we get a higher ratio of operation output from the data center server to keep with keeping the watt at a manageable level. So that's just another example of what they're trying to drive to for efficiency.
And it makes sense,
Yeah,
right? Because at the end of the day, what came out was computations,
yep,
and
yep,
what you put in was a lot of power. And so that's a really good metric, I think. It's
yeah,
it's kind of hard to define, especially since only part of that is the hardware and much of that is the software.
exactly,
And in
exactly.
fact, I worked with a professor in Italy, and I even gave some lectures with him in Italy. But his entire career has been focused on efficient computing.
Mm,
and that's from the code side. And so I think that there's kind of a little bit of a disconnect there.
Yeah,
Everybody's, geared up. Let's build higher power processors. Let's build, faster GPUs and AI accelerators and all that stuff. We don't hear a whole lot about, let's make this code really efficient.
yeah, no,
And so, what's going on that side, I think we have a whole lot less access to. But we're also seeing other things, like you have AC microgrid stability on the list here. And that's a big one. We talk about the voltage to the chip and how critical it is and all that stuff, but we don't really talk a lot about the interconnect at the 48-volt intermediate bus.
yeah,
And so we have these microgrid AC inverters that are distributed around the data center, and those get plugged into these racks. And any microgrid can be connected to any one of these racks. And so, because of the impedance of these interconnects, we're starting to see microgrid instabilities.
yeah.
And that's something I think that, mathematically is relatively easy for most of us to understand, but it's not something we ever had to deal with.
No.
And we're all kind of going, what? How do you even measure that?
I love it. Good conversation around pain points, and coming back around just to center everyone around on the of our audience around what we're talking about, where to apply this power integrity work. Let's just briefly go through the design components of the data center as we're understanding them and speaking to them. We have a diagram up in the upper right showing these racks of servers, and then they're all being fed the DC loads from a common location. And then a breakdown of the server itself and how the data flow of that power delivery network and the energy flow is helping keep that powered. Um, in the middle of it, in a summary, there's a lot of processor GPU activity. There's FPGAs involved. We have SerDes to take care of on that data efficiency side, and then lots of power rails. And I hear it a lot from customers, being able to do dynamic voltage management along with heat management and keeping an eye on the communication side as well is it's really making the efficiency work complex and involving a lot of monitoring and validation. So that's some of the architecture and the makeup of the system that I can speak to on this slide. Anything to add there, Steve?
Well, I think you hit a really good point, and it really is interesting, especially when you get down to the dynamic voltage control. Because I don't know if you guys noticed the news recently, but Intel's been having a lot of trouble with their Gen 13 and Gen 14 processors and instabilities that caused them to lock up. And there was a lot of troubleshooting going on for months before Intel finally said that the problem is their dynamic voltage control.
Wow.
And so the good news is they found it. The bad news is that it's not fixable. Um,
Wow.
and yeah, that's really painful.
Yeah, yeah.
But you look at Intel; they're the masters of this. They invented this dynamic voltage control and all that stuff, right? And they're struggling on their own. So it kind of puts a perspective on the fact that this isn't easy stuff. This is complex, and we'll talk about this more, I'm sure, during this conversation. But you're talking about SerDes, and I try to remind engineers all the time: power supplies don't actually make money, right? I mean, they're not making money in this server. They're powering the stuff that does,
Yeah,
and the stuff that does, for the most part, is transceivers.
yeah,
And so, part of our job is to get these cores managed and get the power done and get the, cooling right and all that stuff. What we're not focused as much on is that the number of transceivers is growing really, really fast. At
yeah,
the same time, these systems are getting really, really dense.
yeah.
And so we're putting the power from the noise from the power systems much closer to the transceivers.
Yeah.
And that's one of the things I think we really have to watch for.
I like that comment on power supplies. Power supplies are not generating cash for these cloud computing companies. If anything, they're generating expense. If they're not run efficiently, those power supplies are drawing money out of their pocket. Um, but great point. Let's get down into the measurements. We love talking about power integrity and we're both test and measurement guys, and the next slide kind of hits on some key measurements. For the viewers, this is kind of a launching point into some more detail. We're going to break down some of these measurement types and go into more detail in future slides, but this is kind of a good introduction. And I love Steve's comment. He added the bullet in the upper right. The performance is different in system from theory or outside at the component level. So, Steve, please take it away on this slide. This is a great setup slide for some of the detail we're going to get into.
Yeah, I see this at all of my customers' facilities. There's some power supply guy that's off designing a power supply in the corner. For the most part, they're using, low cost, not system level simulators like, LT Spice or Simplus or whatever, and they're just focused on their power supply. Of course, once you take the power supply and you put it on a printed circuit board with all the decoupling capacitors and real dynamic currents and remote sense, it doesn't work at all like it did before.
Right.
And we kind of shoot ourselves in the foot by doing it off in the corner, building these models and simulations that we can't transport to the system level. And so that's why I tell engineers all the time, yeah, it may not sound like it makes sense to you to do power supply simulation in a simulator like ADS, but it makes sense when you realize that at the end of the day, you need a simulation model that's the whole system, the power supply in the system. And so I think that we spend way too much time assessing these little boxes in the corners and not enough time assessing them as a
The whole
system.
system.
And I think that's a really, really big deal.
Yeah, that's great. And assessment measurement wise of DC to DC falls in these spaces like the impedance profile, jitter and crosstalk, power sequencing, ripple on the power rail, um, transient analysis. I hear this all the time. Really understanding the timing associated with transient analysis is another critical one. And on the AC to DC side, one of them that stands out for me is AC to DC's stability on the power supply. And I think for that one, we'll just jump right into um, you know one uh, gotcha or something to keep an eye out for, and that's really trying to ensure that your AC/DC supply is set up well to understand voltage regulation. So having a supply source that's reliable and is large enough in size as far as voltage range is really important to help ensure that stability. Any comments around voltage regulation?
So, one of the comments that I'll make is that, we talked about efficiency at the very beginning of this conversation, and
Yes.
everybody's focused on this efficiency. And, we're now working on these DC solutions, these module level solutions, and even the front end solutions that are 97, 98% efficient.
Yeah.
And I don't know how many of our, customers have actually tried to measure 98% efficiency, but it's crazy difficult. And so one of the things that we're worried about is stability of the numbers. And I don't mean AC stability, I mean DC stability. We need everything to stay put while we're trying to record the data and while it is that our system is heating up and all these things, right? So we
Yep.
are worried about that. Of course, we're trying to feed in higher voltages because we want to try to keep the currents manageable and the source impedances to where we can keep them stable and all of that stuff. Um, and also, we want to try to keep this well integrated. So, as we get these system levels up, 1500 watts, 2000 watts, 2500 watts, a lot of our customers are stacking up power supplies and putting them in parallel and learning that power supplies don't necessarily parallel all that well.
Right.
And remote sense isn't all that easy when you parallel a lot of source power supplies. So even from this perspective, in a test environment, we really need to be very careful about trying to keep these numbers accurate and stable. Of course, you guys know this better than anybody,
Yeah.
um, but yeah, we really need to worry about the stability of the numbers.
Yeah. And speaking about the stability point, here's another one, accuracy. I mean, um, you're a big fan personally of accuracy, and having accuracy in the form of extremely accurate number of number of digits past the decimal point accuracy on voltage is incredible. Um, how highlight the importance of this. This has got some of your components on the screen here, but how to really make sure you've got accuracy in your measurements.
I like this slide. I really do like this slide. I'm really known for telling our customers that your test setup is really critical. You need to manage your setup very carefully. And every time you create a setup, you need to make sure that it's valid. And how do you validate it? You have to measure something you know. And so I'm famous for saying that. Before you can measure something you don't know, you have to measure something that you do
Yeah,
and in the same order of magnitude.
yeah.
And it's that last bit that kills you. I did have originally customers saying, I don't understand. I measured a 1 ohm resistor and it comes out fine. And I measured my 20 microns and it seems like it's off by a lot. Um, well, measuring 1 ohm is one thing, and measuring 20 microns is something entirely different. And, you know, um, maybe our listeners don't know this, but PicoTest is actually built on a model of helping our customers achieve measurements that they're having trouble achieving. And
Yes.
so our customers started calling us saying, you keep saying measure something you know. Where do I find a 20 micron resistor? I need 20 micron resistors, you're telling me, right? Where do I get those? And so we didn't really have a choice. We got to support our customers. We had to go off and figure out how you make a 20 micron resistor. And you can see here we made them all the way from, I think, about 1.5 microns. I think we actually have a 1.2 micron
Yep.
resistor, all the way up to about 126 microns. And we stopped there because at 250, we can buy off the shelf resistors. But
Hmm.
now I created my own problem because I said you can't measure something you don't know before you measured something you do, and in the same magnitude. So I made my resistors. How do I know my resistors are right?
Yeah.
Well, I said in the last slide, you guys are the experts in this. So I went to you. I went to Keithley and said, can you measure these resistors for me?
Yeah.
And you can see their measurements there. They measured my 32 microns to 5 decimal places. That's probably close enough. Uh,
Yeah.
now, now we know what the right value is, and so we can go measure that in our setup and make sure that we get the right answer, and feel pretty confident then that we got the right result. In fact, I just published a an article or a blog in my extreme measurements column in Signal Integrity Journal on this exact subject called "Validating the Validator," and it
Okay.
shows how it is that we did this with Keithley, and ultimately we turned these into production resistors. In fact, I just got the first lot of production resistors today,
That's great.
so we're pretty excited about it. But it was really just to solve our customers' need to get their setups right.
Great story. Great story. And for our audience, when we get into the chat, the Q&A at the end, I'll make sure to drop a link to that Signal Integrity Journal article. It's fantastic. Um, the other thing I wanted to add was your comment about what you guys see, meaning Picotest as a company. I've been working closely with you for a number of years, and you get the best of the best as far as the signal integrity, power integrity challenges, or some may say the worst of the worst. The ones that are just the most mysterious and most challenging, from some of the largest companies in the world. I mean, they're coming to you for guidance, and so I certainly learn a lot by interacting with you and your team, Steve.
Thanks. Well, let's just say that our customers don't generally come by just to tell us that everything's great.
Exactly.
So
Exactly.
almost by definition, when a
Yeah.
customer comes to us, they have a problem. And you're right. I mean, this is the cream of the crop of the major technical world. And so these aren't dumb guys. These are really smart guys.
Yeah.
It goes back to what I said earlier. We're all in the same boat. We're all kind of
We're
learning
learning.
this together, and we're all chipping away at the different pieces. And so a lot of our customers, they just walk in here with a bullet under their arm
Yeah.
and say, let's power this thing up, or maybe you can show us what's going on here because we don't understand.
One of the other tips to look out for is make sure if you're measuring noise and you really want to understand low frequency events like voltage droop and creep when you're looking at these power rails, make sure you understand the impact that good DC coupling can do on the measurements. And choosing probes that have DC coupling with offset are critical. Um, there's a power rail probe from Tektronix, and Steve at Picotest also has some additional probe help here. But but keep an eye on DC coupling requirements for these power rail measurements. They're really critical, and I could share this knowing, Tektronix is the manufacturer of both the probes and the scope. We get that a lot. We come in and consult. Customers start out with using our existing passive probes and realize they're having some offset issues and noise issues, and those passive probes come complete with the instrument when we ship the oscilloscope. I think we usually come back and say it's important to get a more specialty probe configuration for these critical measurements, and the power rail probes are a good way to go. Anything to add there, Steve? I know your company, I think we have another slide on that.
I agree with what you said, and all of this is really important. I do have an article called The Ultimate VRM Power Rail Noise Voltage Measurement. And in that, I did show that one of the best probes available is the Power Rail probe. But it doesn't stop there, right? The power rail probe is actually the box that you plug onto the scope, and it has all the electronics in it, and that's where all the magic happens, and that's where all the low noise stuff is. But it doesn't stop there. There's an SMA connector on the front of that now you have to get connected to your board.
Yeah,
And so how you get from that box to the board
yeah,
is really problematic. And I think that what we see from our customers is a lot of generic mistakes. And I'll maybe mistakes isn't a great word because they just don't know any better. But the errors are
yeah,
generally repeated. One is that I think engineers really underestimate the oscilloscope power that they need to measure power integrity. Oh, it is just power. I only need 100 megahertz. No, you don't. You need incredible sample rate. You need really high bandwidth. You need very low noise. And then when you get to the probe, and we show this in our online class, I think the first four classes are dedicated to signal and noise. Um, Depending on the cable that you connect to that
yeah,
power probe, you're going to
yeah,
pick up noise or you're not. And when
yeah,
you get down to the phase lock loop level noise, you see some really crazy things. I had a customer here and he brought his probes and stuff and he connected them. He was seeing all this schmutz on
yeah,
his spectrum analyzer in the
yeah,
80 to 100 megahertz ish band. And he said, I just don't know what to do with that. It shows up in all of the measurements and I don't know where that's coming from. And I said, that's called the FM radio band.
mm,
And what that means is that the shield attenuation of your cables is not good enough for the measurement that you're trying to make, is what that's telling you. And so the probe that we connect on the end and the cable that we connect and all of this stuff, it's all really important. The first,
yeah,
I think it's four classes in our online class are dedicated to signal and noise and how much
great.
just the cables and the probe selections matter.
The other thing that I find too, I love this topic as well because the impact of connectivity and probing is so critical. As a scope manufacturer, we hear a lot about, does your scope have enough sample rate? Does it have enough bandwidth? And I like your comments on that topic. But sometimes the shopper of the measurement system is so focused on the scope's performance, on resolution, sample rate, bandwidth, and forget that you just spent a lot of money buying a very well tuned, highly calibrated instrument, but then you put the probe on it that's got deficiencies, and your measurement error is going to get reflected in those deficiencies, and you'll have it's like having an expensive race car and putting, tires from Kmart, or, name a low brand tire manufacturer. This is kind of that analogy, and we see it a lot. And they'll come to us and say, "What's wrong with this? Yeah, I have this high resolution, high bandwidth scope, but I'm still seeing all this measurement error, and I just don't get it. And then my colleague is getting great results, and I'm not." Well, let's start talking about probes and connectivity. Um, Speaking of connectivity, you guys have done a lot to help save our instruments measurement channels with your DC blocks. That's another way of where you're paying attention. You're helping us pay attention to some of the issues associated with connectivity on these higher voltage devices.
Yeah, so, like I said, we respond to customers' demands and customers' problems. We're kind of mostly a semi-custom, customized type business. But one of the things that we did see is that as soon as the intermediate bus voltage went up, people started breaking their front ends. And I'm really good at what I do, and I've broken my front ends too. You know that,
I
right?
know, Steve. Yeah.
And
Yep.
so after I broke my front end, I said, you know what, this is ridiculous. Somebody needs to make a better DC block for power integrity. And there are DC blocks for signal integrity, but for power integrity, it's really different. We're measuring at low frequencies. We can't tolerate the DC bias effect and AC bias effect that ceramic offers. And there is nothing to protect the instrument. You connect a probe to 48 volts. It's pretty easy to wipe out the instrument. And so we
Yep.
made a few different what we call port saver blocks that include inrush limiting, self-charge, self-discharge. And so it's got all the transient suppression and they're tantalum based, bidirectional tantalum based, so that we don't have the DC bias effect, so that we make better measurements. And we've designed a couple of these because some of our customers are doing work with sensitive spectrum analyzers, and we don't have a lot of information about the front ends of these instruments.
Hmm.
But the spectrum analyzer says 200 millivolts max. And so we had a major customer come to us and say, "Can you make us a DC block like the one that you showed us, but can you
Hmm.
make it so that it doesn't exceed 200 millivolts even during inrush?" And so we did that. A
It's
lot of
been
our
a
probes,
big help.
yeah, a lot of our probes are 50 ohm probes. So that's a straight through probe. You connect it to 48 volts and you put 48 volts on the front end of your scope. It's dead.
Yeah.
Guaranteed it's dead.
Yeah. You're not the only one. We've seen an increase on the service side in our service depot of customers coming in with, hey, I've got a blown channel. And under warranty, we can help them with that. But there's a lot of situations where the repair can be high. So I love this. I've recommended these devices to our application engineers and our service organization as a prescription for
Yeah,
someone
I appreciate that. We use everything we design. I mean, we make measurements here too, so we actually use everything that we make. And these blocks really saved us an awful lot of trouble and aggravation, not only from the repair side, but the fact that they're tantalum, they don't have the DC bias and AC bias effects is just huge.
we talked about power dissipation as a problem area or something to watch out for earlier. Being able to understand dissipation starts with some measurement capability and being able to look at the magnetic properties, the inductance, the magnetic loss. And we have some automated capabilities in the oscilloscope to do that. But dissipation is something to really keep an eye out for. Is that correct?
Yeah, I think that's really, really well said. And as we improve the efficiency in our step down regulators, one of the places that we do tend to have a lot of loss is in the inductor. And so we are very focused on the losses in the inductor. And I think I have an article in Signal Integrity Journal that's actually called Selecting a VRM Inductor. Because we built our own little demo board and we couldn't figure out why the efficiency was so bad. And it turned out to be an inductor, and we custom designed an inductor and we showed the differences. But those also are DC bias dependent, so we need to understand the bias effects. Then, if you go further than that, our customers are starting to learn about ground loop errors, and we need coaxial isolators to block that ground loop error. But the coaxial isolators themselves are also extremely sensitive to bias current.
Hmm.
So we need to be aware of that for our measurements also. And inductance isn't constant, it's frequency dependent, especially in the amorphous materials. And so I think we're spending a lot more time assessing magnetics, but I would say rightly so.
Yeah, and automating that really helps, but very important topic. The other one's control loop response. The stability of a power delivery network leans heavily on this, and I learned a lot about doing a good job of control loop response from you and the Picotest team. In fact, we've got on our website, a whole application note and guidance on how to conduct control loop response and making Bode plot measurements. And it's a very important topic. to pay attention to assess stability of that PDN.
It is. And honestly, this is one of those skills I think that's really been lost over the years, for lack of a better way to describe it. You know, Hedrick Bodie, he wrote his book in the 1950s. You can see my bookshelf behind me. I collect books. I actually have his first edition book.
Wow.
And he talked about what the Bodhi plot means and when it's accurate and when it's not accurate and what's important to us and what we're looking for and all of those things. And I think a lot of it got lost over the decades. And now
Hmm.
some engineers know that they're supposed to measure Bodhi plots. They don't really know how to interpret them. Um, and it's so much easier to make a measurement of control of stability than it was when I started. I mean, now we can do this very well in your oscilloscope, right? We can make Bodie plots in your
Yeah.
scope.
Yeah.
Um,
In
we're
fact,
just we're just not really good at assessing them. But it ties into another article that I wrote that was called "The Inductive Nature of Voltage Control Loops." And if you look at the whole need for capacitors, why do we have so many capacitors on our power boards? It's because capacitors absorb inductors.
yeah.
If we didn't have inductance, we wouldn't need capacitors. We need capacitors to absorb the inductance. The control loop controls that inductance. So we either put a lot more capacitors or we do a better job in the control loop. And that's essentially the choice. And so I think it's really important to understand the control loop response,
Yeah.
how it is to optimize it.
I
And
love
that'll
that.
save a lot of capacitors. And that's important, especially as we decrease the size. Densities are getting tougher.
Yeah.
We don't have room for all these gaps.
Yeah. And you're removing single points of failure if you limit the amount of capacitors in those designs as well. I think,
That's a great point. That's a great point. In fact, in their 2000 amp demo board, every once in a while we lose a ceramic cap. And
yeah.
it's really interesting to see the way that they go, but they're kind of like flash bulbs. Anyway, they're self-clearing,
They're
uh,
self-clearing. Yeah.
but it's pretty wild. So that's actually a great point that I didn't think about. But you're right. Every one of these capacitors adds a point of failure.
Yeah. So when we got another topic to say, let's look at NISM. Steve, you've got me excited about NISM. We're still investigating this as a nice feature to have for our customers, but really getting an idea of NISM to help overcome measurement integrity challenges when you don't have access to the core. You can't measure the system in operation for some reason or another, either physically or safety wise. And NISM helps you get there in your understanding of the measurement's performance. Is that right? Is that how you can,
Yeah, that's
help me
good
learn more
description.
about that? Yeah.
Yeah, that was a good description. I created NISM about a dozen years ago, maybe a little
Wow.
more. Um, and it was mostly for the satellite world because at the time there were so many regulators on the boards, and a lot of them were three-terminal regulators where we couldn't measure Bodie plots. But certainly NASA's not going to let you cut a trace on the board to insert a Bodie plot injector, right?
No.
And so I needed to find a way that we could measure stability directly without having to interact with the system. We need no cutting traces or lifting components had to be measured actually in circuit. And so we did that in 2011. Today, it's more important than ever, and it's just really starting to get popular. It just showed up in QSpice, it just showed up in PSpice. It's in ADS now. It's in most vector network analyzers. But the reason is really simple. A lot of these power rails, and you said, early on in this interview, that there's just so many power rails. We could have
Mhm.
100 power rails on one board.
Wow.
And many of those, we don't have access to the control loop. So how do you measure stability of 100 power rails? We do that using NISM, which is essentially a browser measurement. You
Cool.
measure the
Cool.
impedance, and the software turns that into a stability number for you
That's great.
directly, and we can measure 100 control loops in maybe 2 hours.
Yeah.
Um, whereas trying to do that with Bodie plots, you'd never be able to do that.
That's great. That's a great description of it and a real time saver as well. Sepia is another topic, and this is something that our good friend Masashi has written an article around about improving loop analysis from time domain waveforms using Sepia. So Here's where we touch on trying to assess that large signal stability. Share some insights from here, and you even have a product to kind of help manage that as well on the in-socket loads.
Yeah. You mentioned Masashi. I go back with Masashi probably a dozen years from when he was at Texas Instrument. Really, really brilliant guy. And I'll call him young, which means that he's young compared to me.
And
Um,
me.
but, but he also has some really challenging issues. He works over at Corvo and he does a lot of work on high power pulse systems. And so he deals a lot in the world of large signal response and large signal domain in power. And so we spent a lot of time working with him in Sapia for the assessment of his RF systems, pulse power. In core stuff, AI, um, it's been going on for even longer than that. Maybe about 5 or 6 years ago, maybe even a little more than that now. Customers started hitting this 1,000 amp mark, and they started realizing that large signal was so much different than small signal. They
Hmm.
needed to measure large signal. And so companies like Load Slammer came out and they made their load devices so we could do step loads of high currents. But they had a different problem, and customers didn't really like it. And customers didn't like it because it couldn't do steady state, so it
Okay.
didn't have enough power capability for thermal testing and stuff like that. But also, it wasn't fast enough. So, as experts in gallium nitride, we said we ought to be able to make an ASIC emulator that could do 2,000 amps in really high speed, and we
Hmm.
did. Our load cells 140 picoseconds mounted on the board. We can typically get to about a nanosecond. In fact, our friends at Langer measured our board right at 1 nanosecond. But we started talking to customers when we showed this, and we said, what is the point? We're happy to make it because you guys needed it, but
Yeah.
what is the point? And they said the point is getting missed, but the point is that the chips are getting smaller and the power is going up.
Hmm.
So we're really starting to get concerned about power rail to power rail crosstalk and power rail to signal crosstalk. And we talked
Yeah.
about how many transceivers are on these new boards.
Yeah.
We packed them really tight. And so like we were speaking to Marvell and one of the things that they mentioned is that they may not have this new chip for 2 years, but they're designing boards now.
They have to go now.
How are
Yeah.
they going to get insight? How do they get insight into the thermal issues? How do they get insight into um, this crosstalk,
Hmm.
power rail signal crosstalk before they have a chip? And
Hmm.
so we built these load devices that they can do 66 megasample per second emulation of an
Wow.
ASIC. And the picture you got there is one of my favorites because that is actually white noise. And we can do white noise like that at 2,000 amps peak to peak at
Wow.
66 megasamples per second.
And
And
you can hold it
that,
relatively stable over time. Yeah.
yeah, for sure. And we can even do steady state 2,000 amps for thermal testing. But this is what it's all about. And when you drill into that diagram, you can see these boards at all of the conferences. One of the things that really is shocking to most customers is the response doesn't look at all like they expected. They said, "Hey, we're only worried about the high speed stuff because we're looking at the ASIC." They
Okay.
didn't realize how much of what they see is low speed stuff. Um,
Ah.
you
Okay.
don't get to the high speed stuff until you got through the low speed stuff.
Yeah.
So
Yeah.
you need to survive it all. And again, this is just, Picotest supporting our customers. That's what it is.
That's
This is
great.
what they need. Our job was just to make it for them.
Yeah. And Masashi's article, we'll make sure to include this link too in the chat after this after we conclude here, for all of you
Yeah,
to
he
see.
did a great
Yeah,
job.
he did. He did.
Yeah, he did a great
Phenomenal.
job explaining it.
Phenomenal. And
Um,
speaking of helping your customers, Steve, PicoTest has also been helping with an impedance adapter. I love this little device. Yeah, talk more about how this can really help measure AC microgrid stability. You talked about this one of the challenges going forward, and I think this adapter is really helping customers. And so,
it is. I mean, this again was a customer that came to us. They said they were having microgrid stability issues. They needed to know how to assess them. And I told them the simplest way to assess it is with NISM if you can do it. They're like, great. How do you do NISM on a 400 volt AC line? We got
yeah,
440 volt three phase. power coming in. How do we measure NISM on that? And you know me, I love a challenge, right?
Yeah.
So I went off to figure out how you measure NISM on an AC power line, and we figured it out.
How about
And
a
so it's a
thousand volts
galvanic
AC? Yeah.
1,000 volts. Yeah, it'll go to 1,000 volts AC, and we made this for again for a major customer. It's a
Good.
galvanically isolated 2-port or 3-port system, and it uses NISM to assess the stability.
We're getting close to wrapping up here. Just a few other things. Impedance testing for PDN component response. We talked about this already. Bode plots and looking at PDN impedance with an oscilloscope is another way outside of using a VNA. If some of these power integrity labs aren't, um, you know, uh, able to afford or have a VNA at their disposal, the gold standard, there's oscilloscope-based system capability that can give them that impedance testing capability.
Yes, I've done a couple of different webinars on it. Some even with you,
Yeah,
about why.
right.
And I always ask the question why, because when instrument companies and customers started talking about putting frequency domain measurements into an oscilloscope, I asked the same question. I said, why? We have frequency response analyzers and we have vector network analyzers, so what's the point?
Yeah,
And we went on the road and started talking to customers. And of course, we talked to customers all the conferences. And the answer was surprisingly simple. They have an oscilloscope on their bench.
okay.
They need to use the oscilloscope for a lot of their measurements. They just want to use the oscilloscope for a lot more of their measurements
Yeah,
because they don't want to have to break down settings. Is we talk about large signal and small signal, and now we're telling them they need two different instruments to do it. They're saying they don't want to do that.
no,
They can measure large signal on their scope. They can do that step load response. Why can't they measure small signal on their scope? And the answer is they can.
you can't. Yeah.
Um, and in
If
the
you've
10
got
years,
good signal to noise ratio. Yeah, if the
exactly.
system, yeah,
Yeah, that's where I was getting to, right? I mean,
right.
a dozen years ago, it didn't work all that well.
Yeah,
And, customers were trying to use analog signals that are really tiny. And of course, impedance was getting lower. When you get to stuff like spectrum view, when you get to the noise levels of an MSO6B, you're at the point where this actually works pretty well.
for that small
But
signal.
that's the
Yeah,
only real, yeah, there's two noticeable differences between oscilloscope measurements and VNA measurements, and these are obviously always getting better with time. One is the measurement speed, and the other one is the calibration support capability.
yeah.
And the oscilloscope companies like Tektronix, you'll build in the calibration capabilities as your customers demand it.
Yeah, we've got a nice, also on our website, I'm reflecting it here, a diagram with the Picotest transformers and active splitters and power supplies in the mix to work in conjunction with the oscilloscope setup to make those impedance measurements accurately. So you can do large and small signals with an oscilloscope, and I think you and our customers, mutual customers, have demonstrated that. Um, we're going to close on one last note, and that is the topic around ground loops. Um, ground loops is crying out for better isolators, and what problems happen when ground loops aren't managed carefully? What comes to mind there?
So, what ground loops do is they create offset errors in our measurements.
Yeah,
So in the 2-port impedance measurement, I think there's so much published about ground loops that engineers are starting to understand that. But what we end up with is we end up a measurement of our dot in series with the resistance of our cable shield. It's really hard for people to understand. Wants to make their brain explode. Um, but if we have a cable, a 1 meter cable, the shield
hmm,
resistance might be 10 milliohms. We're trying to measure 10 microohms, and
wow.
we get 10 microohms plus 10 milliohms. How's that going to work?
Yeah,
We call that the wrong answer. About,
yeah,
I think we said it's 30,000% error or whatever it is, right?
yeah,
Um, and how do you resolve that? You need to get a lot of ground isolation. And so we build isolators for that purpose. When we finally got down to measuring 40 microohms, I think there are a couple of papers floating around now on how much CMR does it take to measure 40 microohms accurately. we need a minimum of 85 dB common mode rejection. That's a lot. That's
It's
an
a lot.
awful lot.
That's a lot.
And so we're building isolators to do that. And in fact, even in our classes, we talk about that. We talk about skipping channels in the scope. Scopes are really great. They have about 95 dB isolation channel to channel.
Yeah.
That's not enough to measure 20 microohms. We need to skip a channel. We need to isolate the ground loop. Um, Most other measurements also have ground loops. Engineers just aren't as familiar with them.
Yeah. That's great. I mean, managing common mode rejection ratio is critical. We've seen that too in our isolated probes we sell for wide bandgap measurements. It's not a topic for today's webinar, but the fundamental isolated probe methodology is also being demonstrated here in your high isolation devices. And together they're trying to solve a problem, that is to really manage that common mode rejection ratio effectively. Um, and ground loops do appear in power relay noise measurements too. I mean, if we see ground voltage differences across the ASIC, those are going to be going up because that high current that we're just throwing at that device. And so it's important to really understand isolation for your probing system. And you've got another handy tip or device here that could be used that I think we've got one of these in our lab as well, Steve.
Yeah, this is, again, it's just necessity. We build stuff out of necessity. We're making measurements and our customers making measurements. When you get to this 2000 amp or even 1000 amp level in these, big ASICs, it's easy to get 10 millivolts from one corner to the other corner. You put two
Yeah,
power rail probes, the
easily.
ground loop says that they're going to be elevated by that difference. So, may have a 30 millivolt window to operate this ASIC in, and we just lost 10 of it because of the ground. We can't give up 10 millivolts of our 30 millivolt window. We need to get that back. How do you get that back? You isolate the ground loop. One of the biggest issues in these isolators is, but yes, that's also a high bandwidth signal.
Hmm.
So how do we build something that gives us low frequency ground loop isolation and doesn't screw up the high frequency measurement? So what's special about this particular one is that it goes to 2 gigahertz.
That's nice.
And so it'll
Nice.
isolate those low frequency ground loops, but it won't interfere with your measurements up to 2 gigahertz or
That's
more.
good. And earlier you commented on having higher bandwidth scopes, so higher measurement capability on the bandwidth side. So that's good to hear. Well, we're at a close, and before we go to Q&A, let's just quickly summarize. This has been a lot of fun, Steve. In summary, energy demands are growing in the data center with AI coming in, and to your point, PDN topology is in a complete state of change. There's no rule of thumb. There's no a serial data standard in the power integrity world to define this new PDN topology. So we're, I think, a lot of what we talked about today is just going back to the basics, impedance, control loop response testing, and just putting together a good test system in a lab that can help these companies get greater confidence and prepare for this higher power and higher wattage systems that they're going to be asked to produce and ship and support. Anything to add, Steve?
That's exactly right. I've had so much fun today, Chris. I got to tell you, maybe you see the same thing, but I vacillate between, maybe Mondays and Wednesdays. I wake up saying it's time for me to retire. I'll let the young guys do this. And on Tuesdays and Thursdays, I wake up and say, "Wow, another challenge! I can't wait to do this.
Yeah,
I know how to do this. I can figure this out." And so it's fun, it's challenging, and at times frustrating. But we're all in this together, and this is what we do.
I love it, Steve. It's a lot of fun. Well, with that, we'll close on the presentation and then transition over to the live Q&A. So this has been a lot of fun. Let's keep it going.